Okay, so we wrote two equations for n and theta, and when we divided equation 1 by equation 2, we got that theta is equal to tangent minus 1, or arctangent if you want, arctangent of v square over rho g. So in this way, we can have an approximate idea of what should be the angle to not have to rely on friction, to not go up or down. Okay? Any question on this problem? Okay. Another problem. The design of the skier requires knowing the type of forces that will be exerted on the skier and his approximate trajectory. In the case shown, determine the normal force and acceleration on the 600 Newton skier the instant he arrives at the end of jump A, where his velocity is 9 meters per second. So let us look at the figure here. Okay. So you have a skier going down a path, and the equation of the path is given. Y is equal to 1 over 60 x squared minus 50. You want to find what will be its acceleration when he reaches point A. Okay? So the question is to find what is the acceleration when we reach point A. So to be able to answer this problem, why here we will choose normal tangential coordinates? Because look, you don't have any, if you want, any idea about AX or AY. They didn't give you equations, okay? So what is the advantage of using UT-UN? That in UT-UN, at least you know what is AN, okay? AN is V squared over rho. So here, they gave me the velocity. I know the velocity, it is given. They said that when he will reach point A, its velocity is 9 meters per second. So I know V, and I know the trajectory of my motion. I know the trajectory, so I can get rho. So AN, I can directly calculate it, okay? So this is a positive aspect of using normal tangential coordinates. On the other hand, if I choose to work in X and Y, I don't know AX and I don't know AY. So I have two unknowns instead of one in normal tangential coordinates. And sometimes, if you increase the number of unknowns, you'll not be able to solve your system because you will have lower number of equations. Okay? So here, what we can say is, since we know the velocity at A, and since we know the path of motion, so the best idea to solve is to use a NAT, okay, UNUT frame. Now, at A, how is UT? UT is always tangent to the path, okay? And as you can see here, you know that when you have the equation of the path, to get the tangent, what do we do? To do the tangent, all we have to do is to do the derivative, okay? Because the slope of the curve is given by dy over dx, okay? And dy over dx in this problem, if you derive with respect to x, you get 2x over 60, so it's x over 30. And at point A, x is 0, okay? So at A, x is equal to 0, so slope is 0, okay? So we deduce that the tangent at A is horizontal. So the tangent at A is horizontal. And therefore, you can say that UT at A will be along the horizontal line and towards the left. Why towards the left? Because the skier is going down, okay? So this is UT vector. And UN, as usual, is perpendicular to UT, directed towards the center of curvature. And as you can see here, your concavity is upward. So the center of curvature will be in the upper side. So this is UN. Now here from the figure, it's clear. In case the figure is not very clear, you can do the second derivative. The second derivative will tell you if UN is up or down. If you get a positive second derivative, this means UN is up. If you get a negative second derivative, this means UN is down. Here, the second derivative is 1 over 30, which is positive. So the concavity is upward and UN is up. So this is UN. And for UB here, UB is perpendicular, and I will not need UB here. You know what? Why? UB is only needed if I have forces along UB, but as in the formula car problem. Here, no forces along UB, so I will not use the equation sum of B equals 0. Okay? But I can just present it, so this is vector UB. Now, next step, I will represent the forces acting on the sphere at A. What are the forces acting on the sphere when it will reach A? I have two forces, the weight of A, W, and the normal reaction N. Okay? So the forces are simply normal, the normal at A, and I have the weight of the scale. These are the two forces acting on it. Uh, Michael, did you ask a question? I don't understand what you said.
خلاص, it's nothing, doctor. Never mind.
Okay. Okay. So, as you can see here we represented the free body diagram. Okay. So you have, this is the weight, this is the normal reaction. Okay. And these are your UT and UN. So now we are ready to write the equations along UN and UT. Okay. So first, if I take the UT direction, as you can see, both forces here are perpendicular to UT, so no force component along UT. So the first relation, sum of T equals MAT, will give you 0, since no forces projection on UT. So what can we conclude from this? We can conclude from this equation that AT at point A is equal to 0, okay? And then we still need only to find an, okay? Sorry, we need to find an and an ay, because they asked for the acceleration of a, okay? To find the acceleration of a, in general, it's a vector. A vector is divided into two components, at and an. But because ATA is 0, so the acceleration of a will be restricted to the normal component an of a. Okay, since the magnitude of AA is radical ANA square plus ATA square, but ATA is 0. Okay, so AA vector will be equal to AN vector. And to calculate AN, all we have to do is to say that it's V square over rho. Okay, the velocity is given at point A, it's 9. So we still need only to get rho to be able to calculate AN and therefore to calculate AA. Now how to get rho here? Since they gave us the formula of y function of x, so we apply the big formula we have learned in the previous chapter, which is rho equals to 1 plus dy over dx dy over dx square, and the whole term to the power 3 over 2, yani 1.5, over the absolute value of the second derivative of y with respect to x, okay, of d square y with respect to x. So if we apply this formula in this problem here, okay, and we want to find rho at which point, we need rho at point A. We need rho at A. So it's equal to 1 plus, we said that dy over dx is 2x over 60, which is x over 30, okay? But since A, for ax is 0, so it's 1 plus 0 to the power 1.5. 1 to the power 1.5 is 1, okay? So the first term is 1 over the absolute value of the second derivative of y with respect to x. The second derivative is 1 over 30. And it's positive, so no need to take the absolute value. So it's 1 over 30. So it's equal to 30. Okay? So the radius of curvature at A is equal to 30 meters. Okay? And now, all I have to do is to replace in v square over rho. I get the acceleration, the normal acceleration at A. Okay? Now, we didn't finish because I asked also for the normal reaction NA. This is why to get NA, we will apply sum of forces along UN. So if we do sum of forces along UN equals to MAN, we have that along UN, we have plus NA and minus W equals to mv square over rho. Okay, we have already calculated rho, so all we have to do now is to replace, and we get NA. NA is, so NA is equal to W plus mv square over rho. And in this way, we have solved for the two unknowns, which are n and the acceleration. Okay. Any question on this problem?
دكتور
Yes.
اف اف تي احنا عم ناخد A تحت
Yes.
and forces at
A
A.
مظبوط. A تحت. يعني what are the forces acting on A? When the skier is at A, you have the weight of the skier and you have the normal.
Okay.
Okay. هلا for
لو
example, they can ask you at any position. So هن نقوا the easiest position here. I will do for you a more complex position. If the skier is here, for example, okay, let's say x is given, let's say 2 meters, 3 meters, so they can give me any value of x, and they tell me to calculate the normal reaction. What will I do? So first, what will be a little bit complex is that a ut will be inclined in this case, okay? So let us take a numerical example. For example, if they say x is equal to 3, okay? So let's say for x equals 3 meters, what is the normal and what is the acceleration? For example, okay, for x equals 3 meters. What should I do? First, I say that ut is tangent to the path, okay? And un is perpendicular to ut and directed towards the center of curvature. And since I have an upward concavity, un will be towards, it will be up, okay? Now, in order to continue, I should know the direction of ut and with respect to the horizontal. Who can tell me, how can I find the direction of ut with respect to the horizontal? What should I do? So if I take this position, this is ut, let's say, this is un. To be able to continue and project my forces, you know that the forces here are the same. You have weight and normal, but what will be different here is the normal direction. The weight is always vertical, but the normal is tangent, it's perpendicular to the tangent because the normal reaction is perpendicular to contact, okay? And so since n is perpendicular to contact and the contact line is along ut here, so n is perpendicular to ut, so it's along un. So if I want to represent my case here, this will be ut, this will be un, this will be the weight, and this is the normal reaction, n. Okay, so now to be able to continue, I should know the angle between ut and the horizontal. This one. Because I needed to project the weight. Okay, for n, no problem. N is along UN. But in order to project the weight on UN and UT, I need the angle here. The angle between UT and the horizontal is equal to the angle between UN and the weight. Why? Because the weight is perpendicular to the horizontal and UN is perpendicular to UT. So these two angles are equal. Okay? You can find this by another method. You can say that if this is theta, this is angle theta, and the weight is perpendicular to the horizontal. So if I do the extension of the weight line, okay, it's perpendicular to the horizontal. So the weight is doing with the inclined here, is doing an angle of 90 minus theta, okay, and therefore it will do with UN an angle of theta because the summation of these two is 90 degrees, okay. So the angle between the weight and UN is theta. Therefore, to be able to project the weight on UN and UT, I should calculate the angle theta. And for theta, it's very simple. As we said, UT is always tangent to the path, so it's along. To find its direction with the horizontal, we should find the slope. Okay, so you can say that tangent of theta is equal to dy over dx at point of interest. Okay, so here you are interested for which point? For dy over dx at x equal to 3 meters, because here they gave us an example. I gave you the example that x is 3 meters. Okay, so what you do, you replace uh, in dy by dx x by 3. So we said that dy by dx is equal to x over 30. Okay, so by replacing x by 3, you get 1 over 10. Then from your calculator, you can find theta. Now, once you find theta, what you will do, you will project your forces on UN and UT. So let us do this together. Now, sum of t in this case will not be 0. Why? Because look at the figure. It's true that n is still along UN, but for the weight now, no. For the weight, it can be decomposed into two components. One along UT, which is along positive UT, and one along minus UN. Okay? The component along UT is W sine theta. Okay, because the angle theta is here with UN. So when you project on UN, you do cosine theta, and when you project on UD, on UT, you do sine theta. So if I write now sum of t, sum of tangential forces, okay, what do I have? I have only the projection of the weight, which is W sine of theta, okay, equals to what? Equals to m times 80. Okay, so if you replace W by mg, you have mg sine theta equals to m80. M will be simplified, so you get that 80 is equal to g sine theta. So as you can see, the only particular case where 80 is 0 will be when the slope is horizontal, because theta will become 0 and sine theta will be 0. For any other angle, when going through the incline, AT will not be 0. And of course, when you go down, AT will be positive because you will accelerate. And if you go up, AT will be negative because the projection of the weight will be opposing UT. However, when you go down, the projection of the weight will be along UT. Okay? And to find AN, you do for AN the same procedure. You do V square over rho. Okay? V will be given, and rho, you should find it. So you apply the formula we learned together, but not for x equals 0. You apply it for x equals 2. Okay? And to find finally the normal reaction, what you do is sum of n equals to MAN equals to m times velocity at the point. Let's call it, if you want, b. So if we take point B here, so here for x equals 3, we name the point B. So it's MVB square over rho at B, okay, over rho B, equals to, if I project on UN, what do I have? I have plus N and minus the projection of weight, which is minus W cosine theta. So it's equal to plus N at point B minus W cosine theta. Okay, so your normal reaction here will be, so NB will be equal to MV square over rho plus W cosine theta. Okay, so MV square over rho plus W cosine theta. And in this way, we solve for the normal reaction. Now, if they ask for acceleration of B, don't forget to do the radical, okay? So acceleration of B as magnitude is equal to radical of AB tangential, because here we have two components, AB tangential square plus AB normal square. And if you want to do the direction, as we did previously, you finding AB tangential, AB normal, you can find the angle between AB and UT, and then you can deduce the angle between AB and the horizontal, as we did in a previous problem. Any question on this? Okay, so this is the chapter of second law of Newton. We are done with this chapter. So as you can see, if you understand well the previous chapter, the only new thing in this chapter is that we are applying the second law of Newton. So we are using sum of forces equal ma. Okay, so if you know to deal with x, y, z coordinates and u and ut from the previous chapter, all you have to do here is to apply the second law of Newton and obtain your unknowns if you have unknown forces. And sometimes, as we said, you need to combine the two chapters, because sometimes you find the acceleration and then you replace it back to get the velocity, let's say. Or as we did in the pulley example, you need to find from the pulley system, you need to correlate acceleration. So you should use the previous chapter. And after this, you apply the second law of Newton. Okay. So please try to start review problems on these chapters. I posted the review. They are already posted for you. They are a little bit hard, so don't worry about it. Okay, just try to do as much as you can, and we will solve together some problems. And in case maybe we will not have time to solve all, but I have already recorded videos for all problems, so I can send them to you. Okay. So hopefully Monday we will start the last chapter, which is also very short like this one. And the remaining sessions we do review. Okay?
دكتور للفاينل عندنا shear و bending moment.
Yes. You have shear and bending moments, and you have dynamics for the final.
Is it gonna be online or on campus?
Online.
مثل الإكزامز الفورمات راح يكون.
Yes, same format, yes.
Okay, thank
وطول
you.
دكتور قد
نعم.
قد مدة الفحص؟
It will be longer than usual exams. Maybe
okay.
1 hour and a half, or يعني more than 1 hour, of course.
Okay.
Doctor, يعني just to be sure كل شيء عندنا everything after exam 2 basically.
Yes, everything after exam 2.
Okay, so من internal forces all the way to work and energy. But no, it's the last chapter basically.
Yes, exactly.
Thank you.
Okay. Bye.